In this video, we're going to take a look at what's called the concavity test. I refer to this as the second derivative test. There's actually another second derivative test out there that tells you something completely different. But I call this the second derivative test because of its similarities to the first derivative test that we talked about in the previous video. So, first of all, we need to identify some definitions so that we know what we're looking for here. Concavity refers to if a graph is concave up or concave down. And what that means is, hopefully this is a pretty good visual for that. A graph being concave up means that the graph is curved upward, right? So think about maybe like a parabola that would be opening upward. That would be concave up, right? So I think of it as like almost like water would collect in that. Almost you have like a receptacle there where it would build up in there. So curving upward, we call that concave up. Concave down means the graph is curved downward. Okay, and then a point in which you switch from concave up to concave down or vice versa, if your concavity switches, we call that an inflection point. And you've probably heard this phrase inflection point, not in a math sense, but it's exactly what it means. Is that a lot of times you'll hear people talk about a trajectory of something hitting an inflection point and that completely changing the outlook of the situation, right? So what that means is that an inflection point has changed the concavity of our graph from being a curved up to a curved down graph, or vice versa. Okay, we call that an inflection point. So the concavity test, the way you use that, it all deals with the second derivative. It's very similar to the increasing and decreasing tests, but we do it with the second derivative instead of the first derivative. So I'm actually going to look at this this function y equals x to the fourth minus 4x cubed. I'm going to look at this with both the first derivative and second derivative to show you exactly what we're finding here. So it says to discuss this curve with respect to concavity, points of inflection, and local maxima and minima. Over here I'm going to look at the first derivative. Y prime is equal to 4x to the third minus 12x squared. Over here I'm going to look at the second derivative. The second derivative is 12x squared, maybe 12x squared minus 24x. So in a previous video we talked about the first derivative test, but what you would do with the first derivative test is you would set this to 0 to find your critical numbers, which I will do so here. We would get x minus 3, which means we would have critical numbers at x equals 0 from this and x equals 3. And we would call those our critical numbers. And then what we would do is we put them on a number line. And we would say, okay, at 0 and 3, we would plug in values here. If I plug in a negative, this will be positive, and this will be negative. So that means that we're going to have a decrease there. Between 0 and 3, like 1, that would be positive, and this again would be negative, so it would be decreasing between 0 and 3 as well. And then bigger than 3, we would have positive for both, and that would be increasing there. So we would say, well, it's decreasing from negative infinity to 0, and also from 0 to 3, and it's increasing from 3 to infinity. And then we would say that there would be a local minimum there's a local minimum here at 3 because that's where we switch from decreasing to increasing, right? We hit a low point there. There is no local maximum because both of these are decreasing, right? So a local minimum at 3, comma, what do I get if I plug in 3 again into the original function? That would be negative 27. So there's a local minimum there. And that's what the first derivative test would tell us. Now I want you to see the similarities here when we do the second derivative test, or the concavity test, and what that information is going to tell us. So again, I'm going to set this equal to 0, just like we did with the first derivative. I'm going to factor out, in this case, a 12x. Factor out a 12x, and that's going to give us x minus 2, which means we get x equals 0 from this, and x equals 2. Now, we don't technically call those critical numbers. I remember my high school calculus teacher would call them not so critical numbers, so I'm just going to put those in quotations. It's not technically critical numbers, but we're going to use those in the same fashion that we use the critical numbers. So I'm going to make a number line, maybe, and we're going to use 0 and 2. And just like with the first derivative, second derivative, I'm going to plug in numbers in each one of these intervals. So if I were to plug in -1, this would be negative, this would also be negative. So a negative times a negative would be a positive there. Anything between 0 and 2, like 1, I would have a positive times a negative, so that would be negative there. And bigger than 2, like 3, both will be positive, so we get a positive here. Now, with the second derivative, it does not tell you intervals of increase and decrease. What it tells you is intervals of concavity. So a positive means that the graph over that interval is concave up. A negative tells you the graph over that interval is concave down. So we have that the graph is concave up on the interval from -infinity to 0, and again on the interval from 2 to infinity. The graph is concave up, and it's concave down on the interval from 0 to 2. So, that being said, when we switch concavity, we have possible inflection points. Okay, as long as our graph is continuous there, those are inflection points. So that means we have an inflection point here at 0 and an inflection point at 2 because we change concavity at those points, right? So those numbers over here with the first derivative would give us local maximums or local maxima or local minima, depending on which way the increasing and decreasing worked. Here, it doesn't matter the concavity. If we switch concavity, we have an inflection point. Right? So we don't have to differentiate between switching from concave up to down or vice versa. So there's an inflection point at 0, and there's also an inflection point at 2. And if I want to know what the actual coordinate point of those inflection points are, I'm going to plug those into the original function. Again, that's up here. If I plug in 0, I get 0, so there's an inflection point at 0, 0. And if I plug in 2, I get -16. So an inflection point at 2, -16. So just notice the similarity between the first derivative test and the what I call second derivative test or concavity test. It's very similar in the process. It's just you have to understand what it is you're finding with that test. Okay, so I'm going to look at this graph, y equals x to the 4th minus 4x cubed, and we are going to look at to make sure that our local minimum is correct here, that there is no local max, that we have intervals of concavity correctly, and our inflection points here. So I've already labeled a lot of this stuff for us here, but we do have a local minimum down here at 3, -27. We have an inflection point at 0, 0, and an inflection point at 2, -16. So our graph is decreasing until we get to 0, and then it still decreases from 0 to 2. So that's why we had both decreasing there. I'm sorry, from 0 to 3. And then it increases from 3 to infinity. So that was the first derivative. The second derivative told us that the graph was concave up from -infinity to 0, right? So if I just look at this part of the graph, that is very much curved upward, right? So even though it's decreasing, it's curved upward. And then from 0 to 2, it is curved downward. And then we hit this inflection point here, where I go from being curved downward to being curved upward. Again, it's still decreasing there, but now it's changed its curvature, and we have concave up here from 2 to infinity. So hopefully that makes sense of these inflection points and what intervals of concavity look like.